this whole activity, and this was the result. And let's see what you guys said. Reveal counts. Okay, so I looked at this last class, and I said there's a 21 here. That means people must have answered with the number 21. You guys all think that it's the other way around. 21 people responded with the number 9. So the count equals 21, and the value is 9. And that is the correct answer. That's what it actually is. So last class, I was in this group, and I got it wrong. I was like, oh no, everybody said there were 21 typos. And the reason I was so sad is because I knew that the real amount of typos is 10. Let me show you the typos. Here's the text that I can move down. So this was the text you guys did last class, and it has exactly 10 typos. These are the 10 typos. They're all highlighted. And if the real answer is 10 and everybody said 21, then we're not very close. But the real answer is 10, and the most common answer was 9. 21 people said 9, and the second most common answer was 10. So that's actually quite good. And let me show you what the whole thing is from start to finish. So the first time you did this, I took the mathematized results from last class, and I have made them into a nice histogram so we can see what's going on. So the first activity was read it on your own and discover how many typos you think there are. And the real answer is 10. The real answer is 10. And you guys came up with these numbers. The most common thing was 7. Most people found, or the most common number of typos that were found was 7. And the average is 6.9. So you can see that when one person looks for typos, you're not going to find all of them. You find less than all of them. And you have this spread of people. Some people are extreme outliers, only found 1. A couple of people found 11 typos. There were only 10. I don't know what happened. Maybe they thought another word was misspelled. They're just like eager to say that I misspell everything, which is mostly true. So this was the spread before. And you can see this is not correct, right? The real answer is 10, and you guys got 6.9. Of course, it's biased. It's always an underestimate. It's underestimating the true value. You can imagine if you run out and count snails, you're not going to count all the snails and all that. But here is the corrected data. So I drew the raw on top, and underneath it, here is the corrected data. And you can see the most common answer was 9. The second most common was 10. There is a spread now. Some people are an underestimate. Some people are an overestimate. A couple people even got 17. So they think there's 17 typos in the text. Of course, there's actually 10. And this is the amazing thing that got me really excited. The average of all the numbers you guys put in is 9.97. So even though you didn't catch all the typos, by using the formula, on average, you guys found them all, or you knew the number of typos. So you can imagine how useful this would be to be able to figure out the population of a species of animals without having to catch them all. This is like magic to me. It's like you got some snails, you count some snails over here, you count some snails over here, bam, the number of snails in the room is whatever. Like what? It's crazy. This is like a miracle. But it works, and I'm going to show you why it works in a second. I am so impressed that this worked so well. I did not think it would work this well. This is a real miracle to me, if you ask me. You guys got 9.97, and the right answer was 10. So people were able to figure out the number of typos. And I think the cool thing is it's like equally like there's an equal number of people sort of to the left of the real answer and to the right of the real answer. That's in stats, that's called unbiased sometimes. So if you like this kind of thing, that's what stats goes into. We're going to do the little probability derivation, but how it works in real life is stats as well. Any questions or comments before I show you the derivation of where that formula came from? All right, let's see the formula. So let's get a little blackboard. And this was what we did last time. I guess we can keep working on here. So here is the setup. Actually, I have the setup written down in Mathematize. So I'm going to open this up, this little derivation, and I'll open it up and I will pause this so nobody answers. But here's the setup. So I have the two characters I named Alice and Bob, which is the traditional math name for two people. And in this one, they're working on an essay. You guys were given the essay, but whatever. The essay has n typos in it. The value of n is unknown to Alice and Bob. They both read the document one last time. That's just like what you guys did. Alice finds some typos. Bob finds some typos. How can Alice and Bob estimate how many typos remain? They can use probability. And here are the assumptions. So the assumptions are there are these two numbers p and q, so that Alice will find any given typo with probability p, and Bob will find any given typo with probability q. Let me write this down with algebra. So here's what I'm going to do. So we got Alice and Bob. I'm going to make two random variables. I got x Alice and x Bob, and these represent the number of random variables. Actually, I think they were called x and y. Let's call them x and y. X and y. This is Alice mistakes found, and Bob mistakes found. Okay. And these things, there's n typos in total that they could find. So this is going to be a sum of n indicator functions. I'm going to call this a1 plus a2 plus dot 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 plus an, where an is the event. Let's say ak is the event. Ak equals the event. Alice finds the kth typo. So here k is like a dummy variable for any number between 1 and n, and there's the first typo, the second typo, and so on. AK is like, yes, you found the typo. And the same thing for bk. So Bob's sum is b1 plus b2 plus dot 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 plus bn. Bk equals Bob finds the kth typo. All right, and again, these are indicator functions. So here I'm using the notation that I, for some event E, is 1 on the event E, and 0 off the event E, on the event E complement. And this is very similar to what I did before, but slightly different. Before I was just telling you it's 1 and 0 and what are the probabilities. Now I'm telling you it's 1 and 0 and what is the event. But you'll notice that we were given in the problem that the probability of AK is equal to P, that's Alice's probability, and the probability of BK equals Q. And so you could say IA, let's say IAK, it's 1 with probability PK, and it's 0 with probability 1 minus PK. There is no PK, there's just P. Okay, 1 minus P. Okay, so P is Alice's probability, Q is Bob's probability, and I have these events that are either 1 or 0, and I've encoded them. I've used these notations to write down the events. Before we didn't need the names of the events, so it was okay to just write down I1, I2. But now I need the events themselves. You'll see why in a second. But that's the setup. So this is a sum of indicators. Sum of indicators. And that's how you count things, right? So you want to know how many typos you got right. You 1 plus 1 plus 1 for all the ones that you found. The ones you didn't find, you get a 0. So these indicators are indicating did you find the typo or not, and adding them up gives you the total typos. That's the setup that we got. Questions or comments about this setup? Yeah?
Sorry, could you just explain what IE is again?
Yeah, so IE, for any, when we did the first half of the course, we talked about events and probabilities. And then now we're moving into random variables. IE is a random variable, and it's equal to 1 if the event E happens, and it's equal to 0 if the event E complement happens. So IE is a random variable, and it's an indicator random variable, or also known as a Bernoulli random variable. Indicator random variable. So it's a random variable that is either 1 or 0. And when is it 1? It's 1 exactly when the event E happens. When is it 0? It's exactly 0 when the event E does not happen. Right? And in this case, I'm just using these things to just indicate, did Alice find the typo or did Bob find the typo? So like this one will be 1 if Alice found the second typo, and then it'll get included in the sum. If Alice did not find the second typo, then that'll be 0, and then it won't contribute to the sum. So that it's the same kind of thing as before. I'm just giving a name to these events. Before I just said, oh, it's I2, it's the second one, and now I'm saying the second one is exactly when Alice finds the second one. The reason I need these is because I got both Alice and Bob. So if it was just Alice, like you wouldn't need any of this stuff. But because I got Alice and Bob, I want to keep them separate with 2 labels. Yeah? IAK, so AK is an event. AK is the event that Alice finds the kth typo. So that's either Alice found it or not. So in the space of possible things that could happen, our probability space, sometimes AK happens. That's the event that Alice finds it. And sometimes AK does not happen. And IAK are these things that get summed up. And they are random variables. They're this kind of random variable where I put in the event E to be AK. And here I'm pointing out that because Alice finds it with probability P, this is 1 with probability P and 0 with probability 1 minus P. That's all I wanted to say here, so that we know the probabilities. E is just an anonymous event. So like, this is true. This is a definition for any event E. So for any event E, you can define this thing. And then this is the special case. Special case, E is the event AK. Set E equals AK. So it's the special case. It's a bit like in calculus class, you'll say, I have f of x equals some formula x squared, and then later on it'll be like, oh, f of 2 equals 4, right? F of x equals x squared tells you what to do for any x, and over here I got IE that tells you what to do for any E, and here I put in a special case of E. The same kind of thing. This is like one of the main skills in like learning to read math, is you just gotta constantly be asking yourself, what type of object is that thing? So you gotta know like E is an event. What is IE? Oh, that's a random variable, right? Like this kind of stuff. P of AK, what kind of thing is P of AK? Oh, that's a number. Okay, like this kind of stuff. It never stops. You will do this for your entire math career, and you should get good at questioning what type of object are the things and how are they connected. So great question. Anyone else? Okay, so now that we have this thing, and x is a sum of indicators, and y is a sum of indicators, we've done this a bunch of times now, there's a name for things that are sums of indicators. When a random variable is a sum of indicators, like this, we have a name for it. There's actually one other ingredient we need in order to give this thing our special name, which is that they all better be independent. And very fortunately for us, in the list of assumptions, the next thing is that whether or not they notice each typo is independent for all the typos and between Alice and Bob. So because everything is independent, all these things are independent, the x's and the y's are actually binomial random variables. So x is binomial np, y is binomial nq. So when you add up n things, each of which are indicators with probability p, then that's a binomial np. So therefore, by what we know, x is binomial np. And similarly, y is binomial nq. All right. So far, so good. Now is where things get maybe a little bit tricky, is we look at the number they have in common. The number they have in common. And I called that z, or z if you prefer. Let z be the number of mistakes that Alice and Bob both found. All right. How are we going to write this guy down? Well, here's what the secret is. And this is the reason I had to give everything names. Z is also a sum of indicators. It's A1 intersect B1 plus the indicator of A2 intersect B2. Let me fix this guy up. B1 plus indicator of A3 intersect B3 plus ... all the way up to AN intersect BN. So this is counting. Did Alice and Bob both find the first one? Did Alice and Bob both find the second typo? All the way up to the nth typo. And if you add these up, right, these are indicators, so they're either 1 or 0. If they are both found, this is 1, and then we're counting up the number that they both found. So once again, maybe I'll write I of AK intersect BK, it's 1 on the event AK intersect BK, and it's 0 on the event AK intersect BK complement. So if Alice and Bob both found it, it's 1. If that's not true, then it's 0. Okay. So that's Z. You guys with me so far? Here's the million-dollar question. I can see from this is a sum of indicators. In fact, they're independent indicators. So Z is also going to be a binomial. But the question is, what are its parameters? And that is what I have for you guys to do, to try on Mathematize. Z is also a binomial, but what are its parameters? And if you know this one thing, that'll be the end. Once we know they're binomials, it's very quick to get the formula that we had last class. So let me try to give you a minute here, maybe say a minute and a half. Try to figure out what are the parameters of z. And I'll start this timer here, and then I will open back up this little situation where you can see the formula. You got to find the parameters that go with z. Z is binomial, but what are the parameters? Binomial, question mark, and question mark. That's what I need. Okay, you guys go think. Okay, who would find more time useful? Put your hand up if you would like a little bit more time. Let me give another 30 or so seconds here. Okay, I'm really going to wrap it up here at the end of the timer, so put in your guesses. If you're not sure, that's okay. Okay. All right, let's take a look at what people said. Make sure the timer is not haunting us. And go over here. Okay. Oh. This is a funny thing that happens with my computer sometimes. Look, I'm clicking the mouse and it right clicks. Why would it do this? If this ever happens to you, it's not because there's a ghost. It's because you have a keyboard in your backpack that is being pressed. Okay, so oh, what did it do? Oh my god. This is a real nightmare. We're looking at the code of the page. Okay. All right. Let's try again. Also happens if you have a mouse in your backpack, not like the squeak squeak mouse, like the other type. Okay, I'm gonna stop talking. Z is what? What did you guys say? 54 people out of 62 correctly found the first parameter is n. That's very good. That was the sort of easier one. It's n. Remember, this is the number of things you're adding up. So you got to know how many terms are there in this sequence. They're numbered 1, 2, all the way up to n. There's n of them. Very good. This is the number of things being added up. Number of things. So yeah, like, the classical definition is the number of successes, but the, success can be anything you want. Success is just whatever you're adding up. That's an indicator function. Okay. What about the other one? That's the hard part. The hard part. Oh, I didn't want to do that. Okay, wait, hold on. Let's see. 49 people got PQ, and the correct answer for the second part is P times Q. So that's very good. If you did not get that, let me explain why it's P times Q. So the thing you got to do is identify the number of terms, that's the n, and the number that goes here is the probability that each term is 1. That's what we need. So the parameter we're looking for, is the probability that this indicator function equals 1. This indicator function equals 1. And what is the probability? Well, it's the probability, exactly, of AK intersect BK, right? So if Alice finds it and Bob finds it, that's the probability we're looking for. Then it's 1. Otherwise, it's 0. What is this probability? you have to do one trick to solve this probability. You must use independence. Use independence. Okay, and by independence, this splits as AK times BK. So we were told Alice's and Bob's corrections were independent, and so it splits as a product, and that is P times Q. P times Q. P times Q. So there you go. That's the parameter that goes in the binomial. And of course, this is a real big assumption, right? Like when you did it with your partner, was it independent that you would both find the same thing? Maybe some of them are much easier to find than other ones. Like this is unclear to me though, why this would be true in real life. But if you assume that it's true, then you can get a nice formula. And the thing is, here's the nice formula. Here's the nice formula. Now that we have z and we know all the parameters, so x is binomial np, that was Alice's counts. Y is binomial nq, those were Bob's counts. And z, this is how many they have in common, is n with pq. If you take their means, the mean of x is our classic n times p, multiply them together. The mean of y, this time it's n times q, right? So Bob has this parameter q. How many does Bob find on average? It's n times q. And for z, this is the last thing we just did. Multiply them together. It's n times p times q, because the parameter is pq. So we don't know p, we don't know q, we don't know n, but in real life, you will observe some values for x, y, and z. This is what you and your partner did, right? So you don't know any of these things, but you saw I found 7 typos, my partner found 6 typos, and we found 3 typos between us. And you can combine them to try to squeeze out what n is. And here is in particular a formula for n, a magic formula. N is equal to the expected value of x times the expected value of y divided by the expected value of z. So if you do that, on the top here, you're going to have an np. Let's write it out. Y. np times nq divided by npq. And you see the p's cancel out, the q's cancel out, and one copy of the n cancels out, and you're left with n. So n is equal to the expected value of x times the expected value of y divided by the expected value of z. This is some sort of weird miracle that came out of the algebra, right? And so we could hope, we could cross our fingers and hope that this is approximately x times y divided by z. So in other words, when you, your partner, and the number you have in common, if you multiply them together and divide by how many you found in common, that should give you approximately n. This is approximately, fingers crossed, right? This is what we derived. So the true thing is it works on average, and we just cross our fingers and hope that the numbers are close to their expected values. You might notice, if you are very carefully astute, the actual formula I gave you last class was not x times y divided by z. It was x plus 1 times y plus 1 divided by z plus 1 minus 1. And that's a very slightly different formula, but same kind of idea. So we hope that these things are close to their expected values. This one is really nice because you never divide by 0. If you and your partner found no typos in common, you would divide by 0 here. So these have names. I don't remember the names. You should go to the Wikipedia page, and you will find the names. Gary, do you know the names offhand?
What's that?
The name of these. This is somebody's formula. This is somebody else's formula.
Oh.
For capture, recapture. Let's go to the...
There's a Seaber, Jolly Seaber.
Mark. I believe it's this guy named Mark. His name is right at the beginning. Okay. So here's the first one.
Lincoln Peterson.
There's Chapman. So there's Lincoln. The Chapman one is the one I gave you guys. And there's a Lincoln Peterson one, which is the very simple one. So n times k divided by k, that is the one we have over here. This is Lincoln, Peterson, and Chapman, which are some statistics guys. Lincoln, Peterson. And this one is Chapman. Okay, so these were math people who worked out these formulas. And you too can work out a formula. Maybe there's a better way to combine them. Could be. Didn't you have a student who did this stuff?
Yeah.
Yeah, master's, PhD?
Masters.
Master's. So you can do your master's thesis on this stuff. That's if you want to do that, take more stats classes. Yeah, question here.
Can you go back to the I, A, K, and B, K?
Yes.
For that one, the probability of getting one would be
For Bob, it was PQ. Yeah. Well, there is no PQ. There's P and Q. It's important to note in this problem, P and Q are two different letters. In some problems, 1 minus P is Q, but not in this problem. In this problem, P and Q are just two different numbers.
Okay, so the probability of both of them not finding it.
Yeah.
The binomial should be 1 minus PQ, right? But
Correct.
Would it be the same thing as saying 1 minus P times 1 minus Q because they both, that's a chance they both.
1 minus P times 1 minus Q is that they both, for a given mistake, they both did not find it. So for the first typo, what's the chance they both didn't find it? So when we count them in common, we want to know what's the chance they both did find it, and then we add up the number in common. So yeah, that's important. Yeah, there's a homework question that's like this about P and 1 minus P, and don't get them mixed up. So when you practice that one, you'll see the difference. Yeah. Okay. Hopefully, did I clear it up? Yeah. Good. Okay. Anyone else? All right, so this was the last thing we're doing for the binomial random variable. We're going to learn about a new one called the geometric. That's next. The geometric. So we're going to do some other things and then learn about the geometric random variables. And Gary's going to tell you about this. That's coming up now.
Pass me the mic.
I can give you the mic.
Give me the mic. Thank you.
Okay, I guess we got to.
Let's go set. Oh, yeah, signed on. Go to here. There we go. Okay, first thing I got to add to Mihai's lecture on expectation. He constantly referred to the expected value of x, and statisticians often call the expected value of x the population mean, which they designate with the Greek letter mu. So if you don't know the Greek letter mu, we can draw one of those out in a moment here. I didn't even pull my paper out. That was kind of silly of me. But I'll just grab a piece of paper here. There's some paper. And you want to pronounce it correctly, not moo. It's not a cow. It's mu. And what does a mu look like? This. Something like that. Well, it would be nicer if you could actually see it, right? Let's just take a look at a mu. There's a mu. So you'll see that all over the place when you're in statistics, is that you have a mu, and this is called the population mean, and that is the same, equals the expected value of x. And then another one we use as very common is the population variance is the Greek letter sigma squared. And I did define that. That is equal to the expected value of x squared minus the expected value
You're just
of...
on the edge over there.
Oops, I'm off the edge. I'm off the edge. Yes, thank you. Let's keep that on there. And actually, I'll put it on this one here just to make it easier for that side. Is the expected value of x the quantity squared, or that is the expected value of x squared minus mu squared. Or you can also mathematically show, and this is actually often where we start as a definition, is that that is the expected value of x minus mu squared. So x minus mu is just a function of x, and this emphasizes the idea that variability is this measure of spread about the population mean, and therefore it's this idea that on average how far are our values of x from mu. So I wanted to put that one in, and then I wanted to just drop in a very simple example, and we're just going to set this up. We're not going to calculate everything right now. And I got to go back to an HDMI laptop for a second. Here's an example of a very simple probability distribution, and the question is, what is the the expected value, variance, and standard deviation of x? Now, the standard deviation of x, as Mihai pointed out, is simply the square root of the variance, the non-negative square root of the variance. And if I guess I should emphasize that sigma is defined as the non-negative square root of sigma squared, and that's called the standard deviation. Technically, population standard deviation. We have a sample standard deviation, which we get to when you go into, say, Stat 2040. Okay, so you know how to get the expected value of x by summing up x times p of x. You know how to get the variance of x by taking the summation of the x squared times p of x, and once you have the expected value of x squared and the expected value of x, or mu squared, you can calculate the variance. You can take the square root. You got the standard deviation. I'm pointing this particular problem out, though, because I have given this as a variant of a question in previous stats classes, second-year stats classes, where a lot of people got it wrong, even though it's a very simple question, because they didn't know how to get started. And what's the very first thing you've got to do to solve this question? How many would like to get the expected value of x in terms of c, for example? Does that sound like a good idea? Who says it's a good idea? Let's get the expected value of x in terms of c. Sounds like a pretty good idea. There's a bunch of c's in there. But do we have to do it in terms of c? Why not make your life simpler? Why not solve for c first? How are we going to solve for c first? What do we know about a probability distribution? Or to be a probability distribution, what must you know?
It has to sum to 1.
The probabilities have to sum to 1. And so you can sum those up. And you've got 3c plus 0.7 is equal to 1. And what do you solve for c? 0.1. And then you can put in 0.1 and 0.2 in your table and solve the rest of the problem, right? So that's what I wanted to say, is that this one's easy to solve. Once you say to yourself, hey, for this to be a probability distribution, those things have to add up to 1. So let's solve for c and get that done. I'm going to leave you a couple other examples. These are going to get posted. No need to write them out right now. But here's some others of just some examples for, let me go here. Calculating expected value and variance. And A and B are kind of interesting because this is, again, just a simple draw 2 balls from an urn containing 3 red and 2 white balls. And A is done with replacement, B is done without replacement. C is a little more complicated because it is the sum when two fair dice are tossed. We've done lots with that example. We've done the probability distribution, etc. But can you calculate the mean and the variance for that? Well, you've got a bunch of numbers, of course, because x can take on values from 2 up to 12. And we remember how the probabilities go up and then go down again. So something like this, you might find it, I mean, you can do it on a calculator, but you might usefully use R for it. So if you want to just try using R a little bit, that will be pretty easy to do. And just as an aside, I'm going to throw in this other very simple special probability distribution called the discrete uniform distribution, where x takes on a value of 1 up to k. Okay? And what is the discrete uniform distribution? Well, I didn't even bother with a slide because it was too easy. It was too easy in a way. But the idea of the discrete uniform distribution is that each value of x takes on the same probability. And so if each value of x takes on the same probability and x goes up to k, what's going to be the probability for any value of x? So we'll go back to an example that you used to. Roll a single die. X takes on values of 1 up to 6. 1 up to 6. What was the probability for any single value on the die? What was the value? The value. Any value of x. Roll a single die. X can take on values 1 to 6. What was the probability of each value? What did you say? Ask your friends. This is why you sit beside bright people, so you can just pass it beside them. You say, you know, I was kind of like out of it at that moment. So I was freezing up. What do you think? 1 over 6. How did you know that? Because there were 6 outcomes. K is the number of outcomes. Okay? So if you threw a single die, each face has a number from, well, each face has a 1, a 2, a 3, a 4, a 5, or a 6. There were 6 possible outcomes. The probability that it falls on any face that was a fair die is 1 out of 6. If I threw a 20-sided die and all sides were equally likely, what would you say? It would be 1 out of 20. If you generate random digits, 0 to 9, how many digits are there? There's 10 of them. What's the probability of, therefore, of generating any particular digit, a particular number? It would be 1 out of 10. Okay, so that's the discrete uniform distribution. P of x is simply 1 over k. Write that one down. P of x is equal to 1 over k for the discrete uniform distribution. And think about that. Why is it 1 over k? You've just derived the distribution without writing anything down on paper. You just derived it in your mind. Is it derived in your mind?
Yep.
It's derived in your mind. Good. But we like to have it derived in your mind. I want to just make sure that people are feeling comfortable. People at the back often feel neglected. Are you feeling good with 1 over k? You're feeling good with 1 over k. Everybody here feeling good with 1 over k? Okay. We're good with 1 over k. Okay. So, the answer for D, getting the expected value and variance, is going to be in terms of k. This is not going to be a single number. It's going to be a formula in terms of k. Okay? And then ask yourself, the variance is a little tricky to make good sense of, but it should be easy to understand the expected value of k there. Okay, so let's look at that. Okay, so you've been promised the geometric distribution. Are we going to get it in say 6 minutes? Well, we'll get it started anyhow. Well, I don't want to show you my slide first. I want to discuss what the geometric distribution is about. So let's consider a coin flipping example, okay? Maybe it's a fair coin. Well, let's start with a fair coin. Fair coin's nice and easy to work with. And I ask you, what's the probability of getting the first head on the first flip? What would you tell me? First head on the first flip. You know the answer. 50%, 0.5. Okay. What's the probability that I'm going to have to flip the coin exactly twice to get my first head? Okay, what's the probability of getting that I'm going to have to flip it exactly twice to get my first head? What do you think? 25%. How did you get that?
So it's a 50% chance on the first, and it's a 50% chance on the second. So it's like 1/2 times 1/2.
So what you said, to get the first head on the second flip, I had to get a tail on the first flip. I had to fail on the first flip. So what's the probability to get my first head on the third flip? First head on the third flip. What would you say? 12.5%. You guys like talking percentages, etc. Okay, I'm good with that. Because you said in order to get my first head on the third flip, I had to fail twice in a row, right? I had to fail on the first and fail on the second. In other words, I got a tail on my first and a tail on my second. Now, if I said to you, what's the probability I get my first head on my 23rd flip, what would you tell me? First head on my 23rd flip. What would you say? 1/2 to the 23rd, right? Because you would have got 22 failures, 22 tails and then head. Now what if I told you the coin was biased? Let's go back to 23 flips to get my first head. But suppose there was only a 30% chance of getting the head on any flip. Now what would you tell me? Nothing getting written down. Nothing getting written down. Yep, okay.
2/3 to the 22 times 1/3.
2/3 to the 20, you gave me 2/3. I think I said, what did I say? 0.3 for a head, so 0.7 for a tail. Yeah. So 0.7 to the 22nd times 0.3. So you said 22 tails and then a head. Okay, so let me ask you the question. If I was to flip a coin repeatedly, what's the maximum number of flips I could go before I get my first head? No limit, right? This is what we talk about, countably infinite, okay? So we've kind of caught on to something very different because we now don't have a finite number of points in our sample space. And me and I will want to say many things from a mathematician's perspective about such sample spaces. Okay, so what did we actually just derive? Well, we could have derived it on paper, but let's just take a look at what we just derived in our heads. In our heads. Our heads were so good at this. The probability distribution for a geometric random variable, x can be given by p of x equals q to the x minus p, q to the x minus 1 times p, where x takes on values 1, 2, 3, etc. I have to define my x, my p, and my q carefully here. X is the number of trials required to get the first success. On repeated independent trials, this is important that the trials are independent. And P is the probability of a success on any trial, okay? So I'm using Q in a different way than Mihai used it in earlier in the class. Here it is simply 1 minus p. I use it for the probability of a failure. And so the idea is, if in order to get that first success on the x trial, the first x minus 1 trials all have to be failures. Now, we can make some notes in this, and we're doing this with precision on timing. 2 minutes, 2 minutes. Man, such pressure. Okay. That was all the derivation required. Obtaining the first success on the x trial requires that the first x minus 1 trials are failures. There's a similarity to the binomial distribution in that the trials are independent and they have constant probability of success on each trial. Okay, those are necessary conditions. But unlike the binomial distribution, the number of trials is not fixed. The binomial fixes the number of trials, and counts how many successes we get in those n trials, whereas the geometric, number of trials is not fixed. It's just that we have to go till we get our first one. There's only a single parameter, which is p, one independent parameter, and we simply set q equal to 1 minus p. We'll throw this in, and you can think about why the mean is 1 over p. That's kind of easy. The variance is a derivation that we don't really care about. I'm going to spend a little more time at the start of next class about this. We'll go back to this. And I just want to mention that some software programs like R don't always define x as the trial and getting the first success, but it's the number of trials before you get your first success. So I'll expand on those a little bit next day. I had to move fast. Squeeze it in. Huh?
I think you did a great job for a time of thing.
I had a couple graphs to throw in, but
This will be perfect for next time.
next time. Get a roll next time. So I could